Good evening, everyone. I'm Ankit. I'm a fourth year PhD student at Val Lab. Today's topic would be about neural radiance fields and Gaussian splatting. And the objective of this session is to understand the terminologies that what exists in the literature so that you get aware with the task and the problem statement. And also we'll touch upon little bit maths about this particular field of neural radiance fields and Gaussian splatting. So by any chance, like if someone has read about NeRF and Gaussian splatting before, can I get raise of hands? Okay, so there are few people who know about this thing. So before I proceed, shall I start? So for example, let's start with a very simple thing. Like for example, if you have given a one single image, can you get the 3D of that particular object or particular scene? So for example, in here, if you see that this particular image of sofa, there is some 3D representation that I have got. It's called occupancy map. Similarly, for this chair, we are able to get the mesh. So this is the mesh representation. Similarly, for this bird, this is another representation or implicit representation. So now, if I give a single image, can we get some 3D of it? So it happens that in literature, a lot of people have already solved this. So what they do is a simple DL network where you take this image as an input, you have some DL architecture, and the output of that architecture would be that 3D geometry or 3D representation. And there are different ways to do it. Like for example, this is occupancy grid, this is the mesh, then there are TSDF volumes, then there are parametric models like SMAL and SMPL. So these kind of representations already existed. However, like this is a very difficult problem statement, like getting 3D from just a single view. There was another set of area where people were looking into a different problem statement. So now this is a little bit easier in the sense that I don't give you just one single image. You have been given multiple images of the same scene. So for example, in this particular example here, we have a skull and you have multi-view images of this skull. And what is exactly you want to achieve from it? You want to get the surface, that is the mesh. You want to get that how light is falling onto this geometry and how it is reflecting it back. And there is another problem that you also want to localize the cameras, right? Because you don't have the camera information here. So this is the first step of the problem statement of novel view synthesis. So where we are interested in like getting the surface and the light and reflectance. However, we make one assumption, that is we know the position of the camera in the 3D space. So we'll discuss about it later, but this is the problem setup that you will have multiple images and you actually want to get the geometry and light and reflectance. So in some way it is also inverse graphics problem because you have some RGB with you and you want to get the graphics or the graphics part of it, like how the light is falling onto that particular 3D model, what is the mesh of, what is the structure of that particular surface. So it's like it falls in the category of inverse graphics. And there are different methods, like structure from motion was one method which can give you a sparse point cloud and cameras. The NeRF is something which can give you the radiance field. Then there's one more method popular which is 3D Gaussian splatting, which is nowadays people use that instead of NeRF. But it's good to know about these things as well, like what exactly NeRF did, and maybe you can use it for solving much harder problems after that. So any doubts still here? I think it's pretty simple, right? Okay. So now let us ask one simple question, right? So we all of us we see images in our day-to-day life, right? You have your videos, you have your Instagram where you see different images. But at fundamental level, like what does this pixel value measure? Like what is measured at that pixel, right? So any answers to that? Does anyone know that? Like what does it measure?
Basically measures the image.
Yeah, and in image.
Light
Yes, yes. So basically, it gives some sort of brightness from that particular surface. That is basically it captures, right? So that is what we will like to model now. So now let's just formally define things. So don't get too pedantic about the maths, etc. Just go with the terminologies. So the first terminology is radiance or luminance. So basically, it's just in a unit area, how much light is falling in, is my pointer, okay, how much light is falling on this unit area in a particular direction. That is what this luminance or radiance is, okay. And this is basically a camera model which is there. So you can assume that this is the sensor. So in cameras we have sensors which have fixed area, and this is the optical center of the lens. So the light is coming from somewhere, some direction, and is falling on the sensor, right? Now let us move forward. So ideally, if we have to estimate that how much brightness that particular pixel is, we have to integrate over this over in all the directions, right, from which light is falling. Now to make our life easier, or the scientists in this field, what they have done a very simple assumption that whatever light is falling on the optical center is whatever is falling on the sensor. So that way we just don't have to worry about this double integral, and we can just make an assumption that whatever luminance or the radiance that falls on the optical center, that is what is observed at the camera sensor, okay. So this is just formal definition of that. Any question? Optical center, like every lens has an optical center, right, from which the light passes. Yeah. So basically here we have a camera lens, okay. And another thing is that why this luminance is important for us is because of its directional nature. So for example, if I want to get a 3D mesh, right, or any 3D representation, and so the concept here is that I also want to model that how the light is falling onto it. So to model this, that is why the luminance is very important, because it has the directional component. So it basically models that from which direction how much light is coming. So for example, if we have a lamp there in that particular room and I'm looking at different directions, so I have some model through which I can say that, okay, this much luminance will be coming in this direction or in that direction, or if I'm closer to it, luminance will be higher. If I'm far away, luminance will be less. So that is why this particular property is, or a particular thing is important for us.
So you are assuming that the light falling is like a laser line, something like
Yeah, so we'll assume that there is always straight line. So but in practice it can be from multiple things, but
because from angle also it will spread.
yes. So there are different models to it, and the things get more computationally challenged to solve that kind of things, because even for the simple thing, assumption that light is coming from a straight line, that itself is very difficult. But to model scattering and other such things, it becomes even more challenging. So that is, maybe if you are interested, you can read more things about it. But yeah, people are still solving it. Like for example, if you have a fog, or if you have some water medium or something like that, then how these things, like how can you model such things? Okay, so yeah, so this is one assumption. Now next thing is, so now we'll go into the concept of surface rendering. So for example, let's say our air is medium, right? So our medium is air, and what we want to do is that there is a surface here, okay? Now this surface is emitting some light. So basically, whatever light that comes from here is basically outgoing radiance from this particular point is whatever is falling onto the sensor. So that is the assumption. So if we know that, we actually know the surface and everything can be easily found out, right? But in practice, this is like a very simple scenario, and we don't even know that where the surface is, right? How? Because we don't know where this lambda is. So it's very difficult to model. In case if we know the structure of and where the structure is, then we can make a very good assumption here. Okay. So now the entire process here would be to like what is that particular model we should use so that we can say that if light is coming from some point, how it travels to the sensor. So in next 10 minutes or 15 minutes, we'll just kind of we'll try to figure it out, that how does that happens. And basically we will read about volumetric rendering equation, which was at the core of NeRF, and then we will touch upon NeRF, and then we can go to Gaussian splatting. Okay. So yeah, this was thing. So if the medium is different, then you will have to have different transmission models. So here the scattering is happen, so fog also some scattering will happen, and in this case the medium itself is different, right? So there will be refractions and something else. So now this is what I was saying, explaining earlier, that we don't even know this, what is the transmission medium, and we don't even know where the surface is. So these things are unknown for us. Now we have to come up with a model which can basically basically models that how luminance travels from a long array and falls to the camera sensor. Okay. So to basically model this, we will also introduce one more term, that is called transmittance. Now this transmittance is actually very useful for us because this is unknown to us, right? And we want to model that if light is coming from this point, it might get occluded, right? So we want to model that. So this transmittance is exactly doing that. It basically models that along a straight line, what fraction of light or luminance it reaches y from a point x. So that is what it kind of models. And it has also different properties. For a homogeneous medium, it is something like this, and for a non-homogeneous medium, it is something like this. For our purposes, we will be assuming that everything is a homogeneous medium, and we will be just following this notation. And this is the graph of that. So the blue lines is the sigma, is the density, and this is the transmittance. So transmittance equal to 1 means that it is the light came here at this point, and it is actually reflecting as it is. It is passing as it is. When t equals to 0, it means that it is completely occluded, so the no light will pass from here. So that is the model, basically this model will do. And it has one more interesting property, that is it has this multiplicity, that is a transmittance between x and y can be written like this: t of x comma z, t of z comma y. So you can have an intermediate point and you can then multiply. So it will give you when you are accumulating the this t value, you can say that okay, maybe here some opaque objects were there are some opaque objects were there, but finally when it is reaching here, it became t equals to 0. Here it made 0.5, 0.25 or something like that. So it basically models that how much light will reach.
What was the lambda in the previous slide?
So this is the equation of the line. So you have omega is the direction, so you can, so if you know the lambda, you will exactly know where the surface is. So now this brings us to our first model, that is the absorption only volumetric rendering. So here we will assume that there is no emittance, like there is no light source, and everything is being absorbed. Okay, so this is some medium for which we have this transmittance which we have defined, and this is the light or luminance which is coming from some point xz, and it has to reach to our viewpoint in a direction omega. So you can assume, you can write it like this, that the light coming to x from direction omega is transmittance of x comma xz, which is this medium, and luminance of xz and omega. Okay. So for example, if this is completely opaque surface, then there will be no luminance here, although luminance is coming from some direction. If this is completely transparent or there is no volume density there, then the light that you see, the luminance that you see here will reach here. Okay, this is clear to everyone? Okay. Now this is another simplistic model which is like just an upgradation of the previous model, which is called as emission absorption volumetric rendering. So basically this is the absorption part, but there can be a way, right, where something can be emitted from this particular surface. For example, if light is there but your table is also reflecting something, right? So you want to model such things as well. So that is why we have to consider this into our model, that how much light is being emitted from some surfaces. Now this is the absorption part of the luminance that is coming towards xz. Now for the emittance, which is at the from here to here, you have to do an integral. So basically you want to integrate all the light sources or all the possible light sources here, that how much light will be coming from this particular medium or this particular surface, right? Now this is like pretty hard to find, and we have to do an approximation for it. So that leads to us this volumetric rendering equation, right? So now what we will do is we will approximate this integral within quadrature. So simple algorithm, like from the top level, is that you divide your ray into small line segments, okay? And then for each of the line segment, you contribute its, you basically measure its contribution for each of the line segment there. And if you have that, you can actually model that how much light is reaching the point x from a given direction omega. So so this is the mathematical notation for it. So this is the transmittance, this is the emitted light, and this is another value, the contribution of that segment towards giving light. This is, if people who are aware of nerve, it's alpha. So this is the volumetric rendering equation, and this is being used in nerve as it is. So just to reiterate you what you need to do, you need to draw uniform samples along a ray. You have to compute transmittance between camera and each sample, and you have to aggregate the contributions. Now in this particular equation, one more thing which I want to clarify is, so there are two things which are unknown, like you actually don't know what is sigma, right? And this is also something which you don't know, that what is the color of that sigma. So we will see in nerve when we read about nerve, that these are two things, which the properties which are the sigma, the density at that particular point, and color, the color at that particular point, which then gets integrated over any ray. So now what do we have? So we have created a volumetric rendering, or a rendering equation, for which for every point, pixel point, you can compute density, and you can also compute that how much color would be coming from that direction, right? That is what we have figured out. And if we can render a ray, we can then synthesize the entire image, right? And another good thing is that this is differentiable, so you can back propagate the losses. So this we will see that how it is used in nerve. But any questions so far on the volumetric rendering equation and the models? So what you can imagine is, suppose there is a light source there, so that is giving some luminance, right? And you have some reflective, let's say you have some reflective surface. The light fell into that reflective surface, and it is also emitting some light. Now you have to model such things, right? But in practice you don't know what is the color or all such things. Like you have the pixel value, but you don't know at what density or at what distance that light is being emitted, or at what could be the density of that particular region. So that is why it's an inverse graphic problem, because you only have a pixel value, which would be like an accumulation of all such things. And now you want to dissect it, and you want to figure out the 3D of it. And why you want to do this? So that if you figure out from this particular view, then you can render a novel view, right? This entire thing which we are doing is to create novel views. So what do I mean by novel view? So suppose you take a camera, right, and you just take a capture around this desk, right. In that I only so I did a capture at this radius from the particular object, but I want to see this surface from some other viewpoint. So to do that, I should know the complete 3D of this particular thing that I have captured. So that is why we are doing all this inverse stuff, so that we can know that what is the 3D, or how much light it is coming, how much light is being reflected. So, and once we have this, then you can ideally render a novel view from any viewpoint. Any other question?
Can you go back to where we divide the ray?
This one?
How are we computing? We are dividing a single ray into segments.
Yes, yes.
So how are we computing the contribution from ith segment?
So each of the segment will have its density sigma, right, which basically says that whether there is some volume there or not. Let's say if sigma is 0, then that means it's all vacuum.
Shouldn't the segments that are closer to the camera depend on the segments that are far away along a single ray?
Yes, yes. So we will see that how it has been deployed in practice. So if we talk about NERF literature, specifically NERF, the first paper on this, they did something like this only. So they gave more weightage to the line segments which are near to the camera, and then so they called it as hierarchical sampling. So instead of uniformly distributing the segments, they assigned very few segments for the faraway objects or faraway surface.
So per pixel we are sampling only one ray or multiple rays?
One ray. So then there's another follow-up work which it leads to some sort of aliasing. So NERF for the first paper, then there was a subsequent work called MIPNERF, which assumed that you are not shooting a ray, you are actually shooting a cone. So that the aliasing art, so then you have to integrate over that cone, and they had some approximations for that.
So in this volumetric and what is the information that we have to do this inverse graphics rendering?
So
The illumination part we know
Hmm.
the surface, and the property of the transmission we know.
actually we don't know anything here. So we have to, this is how the loss will get back propagated, and things will come into, it will get
So we only know the final pixel value. All
Exactly,
of the things we
yeah.
are finding on.
yeah, this exactly. So this is what we know.
X.
Like luminance at this,
Luminance at
this is what we know, and this thing can be easily derived from the previous densities. So we'll see that in the NERF paper. Okay, so I'll move forward. Okay, so now neural radiance field. So this was, I think, published in ECCV 2020, and before that also there were a lot of concepts in rendering, like image plane, MPI, multiplane imaging, and so many image IBR techniques were there for novel view synthesis. But this particular thing became more scalable, or had better results than those previous state-of-the-art methods. So, and it's pretty simple, that all you have is just an MLP. So you have an MLP which is parameterized by theta, some weights, and input to this MLP is a spatial location, 3D location, x, y, z, and the viewing direction. And basically for this it will predict two things. One is the color, that how does that surface or that point looks, and density, that how much volumetric density it has, right? So this part is actually very critical here, like the viewing direction. So this you would have seen, right? Like if you have a light source here and you see it from different views, actually the light moves sometimes, right? So the color is also not same from every viewpoint, and these are the good things you want to incorporate in your renderer, or this NERF should actually learn these things, and then you should be able to synthesize such views. So that is the objective here. So the technical term for this is view dependent effects. So you want to model the view dependent effects through this nerve, right? So any questions in this? Okay, so and this is just the volumetric rendering equation that we studied earlier for in nerve. So so this is the color, the final color. This is the transmittance. Alpha is the how much light. So Ti is basically how much light is blocked earlier along that ray, and alpha I is that how much light is contributed by that ray segment. That is this is denoted by this particular quantity. And if you see from here, so you will cast a ray and you will then aggregate over this using this equation, and you will get the final color for each pixel. Okay, so now so now we have this nerve, and all we have to do is we have to train it, right? So how should we train it? So if you remember in the second or third slide which I showed you, that we have multiple images, we have multiple such images. So this is what I am trying to show here as well. So you have this 3D object and you have multiple views of it. So you cast a ray for each of the pixel there, give it to an MLP, then give it to the rendering equation, that is our volumetric rendering. So for any this is the P is the pixel, pi is the camera pose. So for any of the camera pose, and then and the theta which the MLP that we want to learn, you will basically get the final color, and you will just and you already know the ground truth color of that particular pixel. So using this simple loss, a mean squared error loss, you can actually learn your nerve, and that will give you final output. So is the setting clear now for the nerve, that we have multi-view images as input, and we have volumetric rendering equation to render things, and to train the network we use a MSE loss, a simple MSE loss.
In the previous one you have shown that in the previous X, Y, Z, these are spatial locations on the object.
In a 3D scene. So
3D scene.
yes. So how it will work is that initially you will not know anything about a network, right? So but you know the camera pose, so you know where the camera is. So you will shoot a ray from here, and now you will create segments, right? So now for each of the segment you will predict the sigma and the color, like that is what MLP is will do, right? Initially it will give some garbage, so the error will be more, and the gradient will flow, so that it learns that okay, this might be density and this might be the color for this particular segment.
So you need to have ground truth for each of the points on that line.
No. So that's what, you don't need a ground truth for the points, you just need the final ground truth, that what is the pixel at the pixel level, that how much that this is my particular ground truth pixel, and from this I have taken an array and I make, let's say, n segments. Now these n segments will be given to my volumetric rendering equation, which is nothing but summation of I equals to 1 to n Ti alpha I Ci. Now I don't know initially that what is the color of each segment, right? Even the density is not known, but because of the gradient it will learn automatically. And plus you have multiple such views, like the views, you don't have 2 views or 3 views. For a simple nerve it used to take around 100 views of that particular surface.
So you're relying on the physics to get the actual point.
Yes, so we are relying on this, so we are shooting the actual ray in the 3D scene, making the cuts, and what we are relying is that because we are providing multiple such views, so the model or this f theta will automatically learn how to encode it. Yeah.
In the previous one, that XY and XYZ and theta phi we know the direction because we are facing that angle. How do you know XYZ?
So that's the segment, right? These are the points. This is the actual 3D points. So the ray is along 3D points.
Okay. So from each of this point is each of the XYZ.
Yes. So for each of the point that you have created by creating a ray segment, you will give it to an MLP. Direction also you know, and you also know the XYZ of that particular 3D point. So you will be predicting the color and the density for that particular 3D point. Now, once you have it, then you will accumulate it, right? Pass it through the volumetric rendering equation. In that, you will have to compute Ti and alpha I in such a way. So you have the sigma I. Sigma I is being predicted, right? So what will happen is eventually over the time of this training, everything will it will go to a minima where it's kind of it kind of agrees to all the multiple views, right? And then once you have it, you can then synthesize any novel view. So like this is clear to everyone, right? Okay. Now let's okay, this we'll come to this later on. So now let's see what kind of representation NeRF learns, like why is it important for us, right? So if we have a 3D mesh, right? So 3D mesh actually it is kind of discrete, it's discrete in nature. You have triangles and you wrap a texture around it, and because of that you are not able to synthesize very good novel views, and view dependent effects also you are not able to model in the 3D mesh, right? Whereas in NeRF you can imagine this as a continuous voxel representation. So it's very dense, because ideally you can make for any 3D point you can query the MLP and you will get the density and the color for that particular 3D point. So it's a continuous in nature, and that is why it is so popular, and it was very popular in the novel view synthesis task. Okay, so this is what we have. So we have input images, like lots of images from different viewing directions, and then there's one more thing which I discussed in the second slide, right? That we have the geometry, we have the light and the reflectance, and we also want to localize the cameras. So for NeRF, NeRF doesn't do it, doesn't localize the camera on its own. So you have to run a call map to extract the camera poses, and then based upon that only you can do the further algorithm of NeRF, right? So you will define an MLP, and then you will take the reconstruction loss from different views. And once you have it, you can actually render any new view from any viewpoint. You can go closer, you can zoom out, you can have dolly zoom kind of effects, all those things you can do. So yeah, there's one more thing to it. So initially when the authors of NeRF, they were trying, so they used to give 100 training images, and this is the structure of NeRF. So you have linear layers. So so the architecture was such a way that it will take X, Y, Z points as input, and after the fourth layer also they used to have X. Again they used to push the X, Y, Z coordinates, and at the second last layer they used to predict the density, and here they used to inject the viewing direction and then predict the final color. So when they did all this, they observed that the renderings were not very good, like they were coming very bad. If you can see here, this is like very blurry, and this defeats the entire purpose, right? Like we are trying to say that we are integrating and all such thing, and the outcome is so blurry. So they went to this thing called as positional encoding, and this is a very nice paper. If you're interested, you can read it. So now forget about the NeRF and the 3D part of it. Let's say we have a single image, okay, and I want to learn this image through a simple MLP. So you will give, instead of 3D point, you will give pixel points to this MLP and extract the color. So when they gave us the standard u, v pixel location to this MLP, they got a very blurry output, right? So then they tried a different thing. So basically they did a positional encoding of the pixel locations. So it's a normal sinusoidal encoding, and when they did that, they observed that the high frequency details which were missing earlier, they started coming, right? So it's just a representation here. So if you can see, this blue line represents without encoding, this is with encoding. So you can see that with encoding itself, in very few iterations, I was able to get a very high PSNR, right? Whereas this did not even like it's still between 20 to 22.5, even after 5,000 iterations. So this basically showed that if you give encodings to your locations or to your input signals like x, y, z and theta, phi, you can actually increase the representation power of your MLP model, right? So the authors of NERF, they exactly did that. They took the encodings from here and applied the encodings to the position x and the omega, and then they observed that the high frequency details, they started appearing in the final output, in the final novel views. And there's one more technique which NERF did. It was, any question in this slide, like the position encoding part? That's clear, right, to everyone? So now next thing which they introduced in their paper was uniform to hierarchical sampling. So what exactly does it mean? So basically we have so much computation power, right? We don't have enough computation power. Like ideally I can make cut at very small segments and I can compute, but it will be very slow, right? Now to accelerate this, what they did was they defined a coarser strategy first. So instead of having small segments, first you kind of divide your array coarsely, okay? And when you will divide your array coarsely, what will happen is you will get some idea that density is more here or density is less here. And then in the second pass, you do much finer sampling in the regions where density is more. So for example, here the red points are basically this red part. It denotes that the density is high there. So in the second pass, the model will make or sample more points from here. And it makes sense, right? Because if I have a 3D scene like this, what is the point of inferring at this vacuum, right? I want to infer at the exact surface, right? That is more intuitive to my model as well, right? I want to make, I don't want to waste my computation on vacuum points. I want to make my computation towards the region in the scene where density is more or where the occupancy is more. So this was uniform to hierarchical sampling, and it basically accelerated the final, that reduces the training time. Yeah.
So like in this, so first you train with uniform sampling, and after everything trained, then you train it once again with hierarchical.
No. There are two passes. Now to do that, they have a coarser. They have two networks. One is the coarser network, and then there is a finer network.
But because at the start of this training, your density values anyway will be not that good, right? So
Yes.
then how do you decide that should I sample it? So they both will train simultaneously.
So after one iteration is done, then the weights from the coarser are transferred to the finer.
Like
The predictions are there. Yeah.
densities are transferred here and there.
Yeah.
Is it not better to just train one after the other, like train the uniform one good and then?
So this was the very first work, and people have actually improved over NERF. So there were subsequent works in MIPNERF, ZipNERF, MIPNERF, so many, like no one uses the base NERF. Like for faster thing, people use instant NGP, but the fundamentals are same, like of this hierarchical sampling or position encoding. So those things are the same. But you can have train it a different way to optimize your overall training time. And this is another thing, I think one student mentioned it in the beginning of the lecture, that it makes more sense to sample more near to the camera viewpoint, because my background I can't sample at sky, right? It's at infinity. So it's better to sample more near near to the camera and sample less at the background. And this is called as inverse depth sampling, and this is very useful for real world scenes. So for real world scenes, like this kind of sampling strategy is used. So if you will train any instant NGP or any NERF architecture, you can actually say that which kind of sampling you want. and even data loaders are different for based upon the if you are working on synthetic objects or real world objects. So yeah, these are some of the renderings from NERF, and these are for real world scenes. So you can see that like it's able to get those view dependent effects which we discussed earlier, and the quality is also good. Another thing is that because you have some understanding of the scene, right? That is what we were trying to do. So we also get the depth of like some sort of depth of that particular scene. So if you have the depth of the scene, you can do some cool applications, like you can do insert some stuff, and you can, as you can see, because the depth is known for this, so you can place any object in this particular scene. So any questions on NERF? Yeah, so in depth, I'll just go back. So what they do for depth is they just integrate so if you don't use color, if you just integrate this, you will get the depth of the particular scene. So this is called as expected depth. It is not the real depth, because for that is different. But it has some idea that okay, there are the density is more here or the density is less there. But it's not the exact metric depth. Yes, implicitly yes. So if you see, this is what we are trying to do, right? It predicts output color and output density. So density means that what is the probability of having a surface there. So then you kind of integrate it. So one thing is that it's not like it will give you some views, but if you want to get the exact 3D mesh from NERF, it's not possible. Like you have to do something more to get exact 3D mesh. Yes, we do have, but if you for example, to get 3D from the point cloud, you apply this marching cubes algorithm, and another thing is this NERF, right? It has a lot of floaters. So even if there is some vacuum here, it will give it some density. So then you have to apply some heuristics, like okay, I will threshold and I will only keep these densities, and then apply the mesh algorithm. So there are subsequent works on this, like baked SDF, MRF, or such things were there to get the exact mesh. But the task here is the novel view synthesis. Like it's good for novel view synthesis task. Like if you want to just view it from anywhere, that's it. That is the major task here. So the mesh is not the task here. So any other question?
For the input that we are inputting the multi-views, are we also assuming that the lighting conditions remain same in all of those?
So you are saying that the light is also moving in the scene?
Yes.
So there are different models for that, like the base NERF or the base NERF models, they cannot do that. So if something is moving in the scene or there is some local motion and such things, for that there are advanced techniques, like there is a paper called NERFIes and HyperNERF for dynamic scenes, and then there is a paper called as Wild NERF for such things. So there they used to do a scenario where, let's say you are capturing Taj Mahal and you have some images captured in the morning and some images captured in the evening, right? So the lighting has changed. So how to model such things? So the paper name was Wild NERF, and they actually modeled that. You have to do something extra to do that. So what they used to do was they used to have a latent for each image, which will basically measure the appearance or condition the appearance for each multi-view, and then based upon that latent you can generate novel views and do, like they even showed you can do seamless transition between evening to morning or morning to evening. Such things they used to show. So any questions on NERF? If not, then we'll move to Gaussian splatting. So sorry.
How does depth map help NARC to create 3D scenes?
To create 3D scenes, because you can take it from different views, like you can have different. So depth map, I didn't understand the question, like can you repeat?
How the depth regularization helps the NARC to get better 3D scenes?
Oh, okay. So you want to supervise with depth as well. Is that the question? Yes. So there are works. So suppose you must have heard about this Kinect sensors, and even our cameras right nowadays, they have some sort of DTOF sensors or TOF sensors are there. So basically these sensors give some depth. So if you have that, you can actually, the nerve is learned through MSE loss, right, on the color values. You can then also enforce a loss on the depth values. So you get the sigma. So there is a way to rasterize the depth as well. Then you have some depth here and you have the actual depth. Then you can actually take that loss and it will work. So there was a work called as depth nerve. So I don't remember it now, but people have done it. So they have actually used supervision to, and the thing is, if you do that, your training speed will become, your training time will reduce a lot. Because here we don't have depth, so the training time is more. So for example, nerve used to take around 12 hours to train. But there are faster versions of it like MIPNERV and such things which can do in half an hour. But if you give it depth information as well, then you can even train them in minutes. So now we'll move to Gaussian splatting. So seems like nerve came in 2020, and by I think 23 people like the community shifted towards Gaussian splatting, and there are different reasons for it. So so now to motivate that, so what is the bottleneck in nerve, right? So you have this volumetric rendering equation. Now that rendering equation demands that you shoot a ray for every pixel, right? And then for every ray you divide it into some n points. You do those n predictions. So that way, if you see your rendering time, or if you want to render high resolution images like 4K images or 8K images, your rendering time will increase a lot, right? So it will depend upon the number of pixels into how many points you have along a ray, right? So it will be very slow. So even though there were techniques to reduce the training time, but fundamentally because of the volumetric rendering equation, there you cannot, the FPS of the rendering was very low, right? And before the CDGS itself, people started looking into explicit representation. So NERF is an implicit representation because everything is encoded or inside MLP, right? And you have to query different points from that MLP to get the 3D of the scene. So people had started exploring these explicit representations like instant NGP, planoxels and all, which did not have this MLP. They assumed that you have a volumetric grid, and this volumetric grid have some features, and then you kind of interpolate them and then give it to an MLP to predict the color and density. But that also was not sufficient because fundamentally everything was with this volumetric rendering equation. You have to do this part. So I think this was Sigraf's best paper, 3D Gaussian splatting, and it came from George Dratakis group from France. And if you see here, in the teaser image, they have shown the FPS for different nerve representations. So for example, instant NGP 9.2 FPS, training time is around 8 minutes, PSNR is 22. So planoxels is another frames per second. PSNR. So pixel to signal, like, yeah, peak signal to noise ratio. And MIPNUF 360 FPS is even low, but training time is also very high. And this is Gaussian splatting. So training time is also very less, 6 minutes. PSNR is also very high, and FPS is 135. And this is another variant of their 3DGS in which more number of Gaussians are there. So their training time is around 1 hour, but FPS is also still very high, 93 FPS. It's still very high from all the competitors. So because of this particular fact, like it gained traction in this community of novel view synthesis, and now I think it is everyone who works in this domain, like by default they use Gaussian splatting as a representation. No, no one uses NURF any longer. Yeah, so for example, in novel views, I can have a trajectory, right? So suppose I have this object. I will define a trajectory here, and then I can compute FPS for that. So that way, this is how the FPS is computed. So they define a trajectory around a 3D scene, and then you have to see how fast that that scene gets rendered. So that's what. So suppose in this trajectory, if I had 100 frames, so this can do it in very fast. Whereas these methods, they will do it in minutes, right? And some methods will do it in even hours, which is not desired, right? We want everything very fast. So now the fundamental problem setup is same. You have an underlying 3D scene which you want to model. You have the camera poses, and you have the multiple images for that, and you want to in the novel view synthesis task, you want to generate more such images along different viewpoints. So yeah, this is I think I discussed that briefly in the NURF as well. So to get the camera poses, you pass it through a structure from motion algorithm, and that will give you a sparse point cloud. So something like this, and it will also localize the cameras for you. So if you want, you can do a very cool experiment. You can go to your hostels, or you can go to your department buildings, take some photos, pass it through this call map, and you will actually get a very sparse point cloud of that particular structure, and you will also get the camera poses, right? And if you remember NURF, it utilized only the camera poses. It did not make use of any sparse point cloud. So we will see in Gaussian splatting, they actually make use of this this initialization, the sparse point cloud, and they show that basically helps them in achieving faster, reducing the training time. So here again the problem statement is same, that we know the camera poses and the images, and we want to reconstruct this 3D representation so that we can render the novel views. Okay, so we can skip this, maybe we can come to it later. So let's so what does this 3D Gaussian exactly mean? Like 3D Gaussians is actually it's actually a very good representation in the sense that it's explicit. So in NURF, everything was implicit, right? I never knew that, okay, which 3D point has occupancy. I have to query a XYZ point. So suppose if you have to find, if I asked you a question that please give me some points which are high, which have some high density. So you have to do some search, or you have to define some search, right? Whereas in 3D Gaussian, it is intuitive. Like where your density is, there is a Gaussian. That's it. And wherever there is no density, there is no Gaussian. So that is why it's an explicit representation. So for example, you can imagine that if I have a table here, so there will be a lot of Gaussians here, but there will be no Gaussians on the vacuum here. So that is why this is called as an explicit representation. And this is a very nice slide for that. What does this 3D Gaussian do? What are the parameters of this 3D Gaussian? So the first parameter is the position itself, that where exactly I want to have this Gaussian. Then the covariance, that how big the Gaussian should be. So ideally, if I have a bigger object, I want to have a bigger covariance. For smaller objects, smaller covariances. And apart from that, you have the alpha, which basically says that the opaqueness of that particular Gaussian. If it is very high, that means it's completely opaque. And you have then basically in NURV, we saw that we have theta comma phi. We used to give it to the MLP to get the view dependent effects. Now you want to have similar effects here in Gaussian splatting. So they utilized a very well-known concept in graphics called as spherical harmonics. So they utilize this spherical harmonics to model the view dependent color. So spherical harmonics is nothing but, so you can imagine that you have a sphere and it basically models that how the light falls onto this sphere. And you can decompose it, like if you guys know about Fourier analysis, right? You decompose a signal into Fourier weights. Similarly, you can decompose radiance into different set of weights and you can reconstruct it back. So this detail you can maybe check out after the lecture, but you can imagine that there is some concept, spherical harmonics, which can model the view dependent color. Okay, and this is the representation of one such 3D Gaussian. So you can see here that you have a human, and we have plotted the means of Gaussians here. So it's just like any other point cloud, right? There are different viewers as well, so you will also have some covariances and all. So in those viewers, you can see that this Gaussian will have more area or more support, right? So any questions here, like what like the modeling of the 3D Gaussian, is that clear? Are you guys able to relate it with NURV, like how it can handle the view dependent colors and stuff like that? Okay. Which one? Okay. So in this, density is explicit. Okay. So wherever you have a surface, there will be some 3D Gaussian. That is one thing. Another thing is that in NURV, we saw that we have theta comma phi to model the color, right? The color used to change as you used to change your camera viewpoint. Now you want to have something similar here. So for that you use spherical harmonic coefficients. So those coefficients, so based upon the viewing direction, it will give you different colors. So each Gaussian, so we have now a mixture model of Gaussians, right? So it's not just one Gaussian. So for every, so there are Gaussians for the head of the human, then there are Gaussians for different regions in this particular scene. Now for each of that Gaussian, you will have these properties. Okay. Now we will see that how it basically in NURV we had rendering equation, right? Volumetric rendering. And that volumetric rendering has a particular name called as ray tracing. So you trace a ray, whereas Gaussian splatting, it is the other way around. You rasterize something. So you don't do a ray tracing, you do rasterize. So that is why it is faster. We'll see that how that happens, but the fundamentally two representations are different in this sense only, that one works on ray tracing and one works on rasterization. So we will see that how this mixture of Gaussians, it goes through a rasterization process to give you the final image.
How do we train the model to get all these Gaussians?
Yes, we'll come to that. So this is the overview. Okay. So if you remember, I showed you these SFM points, right? Structure from motion points. So that is your first point. So because you have to start from somewhere, right? So you will start from this initialization from structure from motion, and you will initialize 3D Gaussians there. So now you have basically set their positions you have set, and covariances and all you will make some randomly, you will initialize them. The spherical harmonic coefficients, covariances, opacity, you will randomly initialize. And then you will, for any camera viewpoint, you will do a projection, okay, of this Gaussian to that particular viewpoint. Then you will pass it through a differentiable tile rasterizer, so rasterization process, you will get an image, and then you will take a normal reconstruction loss similar to NERF. So we will take a reconstruction loss, the gradients will flow back, and that for particular 3D Gaussians you will update those particular set of properties. So the opacity and the spherical harmonic coefficients, the covariances even, they will get basically updated in this step. Now one fundamental question is, the sparse view, this SFM point is sparse, right? And then how do we get a very good representation, right? Because there will be holes otherwise. So the authors of NERF, they proposed an adaptive density control algorithm. So what exactly that this does is that over the training time, so let's say after 500 iterations, I will analyze the gradients, and based upon those gradients I will add more Gaussians or I will remove more Gaussians. So what can happen is, there can be two things. One thing can be like some Gaussians are like really not required. It might be possible that you might have some Gaussians in the vacuum, and for that color is very random and opacity is always 0. So you don't want such Gaussians in your representation, so you will remove them. Other way can be like, maybe initially you are assigning, you have one Gaussian for this laptop and this table. You don't want that, right? So what you will do is you will split this, and you will have then one Gaussian for table, one Gaussian for laptop. And there can be some other scenario where you want to, let's say you have this floor, but a very tiny Gaussian is representing that. So you want to increase the size of that Gaussian. So you will have, they have such heuristics based upon the gradients of from the loss function. So they analyze those gradients and they kind of add more Gaussians and remove some Gaussians which are not required in this adaptive density control step. So another thing is that from the paper perspective, like a lot of methods have come on how to improve this adaptive density control. So because this part is almost fixed, like no one touches this unless you have very good knowledge in graphics, because this employs a lot of CUDA kernels and stuff like that. This is where you kind of make some sort of heuristics and want to converge faster, because ideally if you have you want to converge faster, so for that you want to quickly explore the scene, right? Because SFM will give you sparse points, so you want to quickly go to chairs, you want to quickly model this tables, ceilings, floors. So you want to quickly go to the surfaces, assign some Gaussians and learn them. So a lot of work has come. Even our lab also have one such work which is under review. So we kind of do Gaussians in under 2 minutes, whereas 3DGS takes around half an hour. And that is very useful because you want to render highs like 4K, 8K, you want to model 4K scenes, 8K scenes, and it will be very useful for different applications. Okay. So this is the formal definition of the Gaussian field. So each point effectively represents a limited area which is in space close to its mean. So and it has some so it resembles like a normal PDF, like a multivariate normal PDF, and you have the covariance matrix. Now here you want the matrix to be symmetric and anisotropic, which means that you can have different ellipsoids. So if it is isotropic, then you will only have spheres, but because of it's anisotropic, you can have ellipsoids. So you can have maybe some Gauss ellipsoid which are like this, some in some y direction, some are elongated in z direction. So you can have different type of Gaussians. And another thing is they decompose this covariance matrix based upon the rotation and scaling like this. So rotation means that from the base canonical representation of a Gaussian, how much it is rotated. Scale means what is the scale, how big it is. So they kind of decompose your covariance matrix like this. So these are some notations, maybe you can read about them in detail later on. And so this we have seen, right? This is the volumetric rendering equation. So here instead of ray tracing, they say that you have a splat. You project the 3D Gaussians to a 2D image plane, and then you compute the color of the pixel. So we'll just go to that. So what happens is, so you have this 3D volume. So there's a concept in graphics, like you have, you can create splats. So splats is basically some sort of primitive, like you can splat triangles. So a triangle in a mesh is also a splat. So basically, if you have a 3D mesh and you keep two 3D meshes like this, you have different splats, and then you kind of rasterize them, and you will get the final image. So similarly, what they have is, you have a 3D Gaussian, right? And this is my camera. Now I want to render this 3D Gaussian here, right? So the first step is to project this 3D Gaussian to 2D splats, right? So they will create this 3D Gaussian, convert it into splats, and then they will do the rasterization process. Okay, so that is the fundamental for it. So for example, this is the very well-known paper, EWA volume splatting in 2001. So given the covariance matrix in world coordinates, and you have your world to cam matrix, cam to image. So these are some notations maybe which you would have read in your maybe DIP, digital image processing course, right? Normal pinhole camera model, you have intrinsics, you have extrinsics or something like that. So in that you will have, right? So first you have to go from world to camera, you have to multiply by camera extrinsics. Then once you have it, you can project this 3D world into image plane using camera intrinsics. So this is particularly like that. So your W is the world to cam matrix, which is the extrinsics, and J is the Jacobian of the camera to image. So which basically means that how you, so from this camera viewpoint, how will you take it to the image plane? So these are the intrinsics. So this paper is a well-known paper which was there in 2001, which came up with this equation and simple assumption that how can you convert a simple 3D world covariance into a 2D covariance. So 3D Gaussians, or the authors of this 3D GS, they utilize this particular thing. They took, you have the covariances right here, this one. So you have the covariance of a 3D Gaussian. So you fit into this equation, world to camera is also known, and the camera to image is also known, because we know the intrinsics and the extrinsics. So extrinsics are coming from the structure from motion, the localization of the cameras. Okay. Now once you have this, so what you have done is you have converted this 3D Gaussians into different 2D splats. So what you have to do is, you have to now do an alpha blending. What can happen is, you can have multiple splats, right? So you can have some 3D Gaussian here, 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 and here. And once you splat them according to a viewpoint, there will be multiple such planes. Now you want to blend them in some way, because some planes can be opaque, some planes can be transparent, some planes can have maybe some semi-transparent, such things. So you want to do an alpha blending. So that is very much similar to the volumetric rendering equation, that you take C1 is the color of that splat, alpha 1 is the contribution. So you do a weighted average of all the splats. Is this clear? Like, is this making sense? Alpha is not, we'll see, we'll go. So C is learnable from a spherical harmonic coefficients, right? Alpha is not, so alpha also, if you remember, we have this opacity term, right, in the Gaussian. So that will define that how much a surface is opaque or transparent, and based upon that the weights of this alpha will change. So go back to the transmittance part. So in the transmittance, it basically said that, right, that how much light is being blocked. So similarly, this alpha, we will see that how much opaque the surfaces were earlier. And let's say if you have some opaque surface here, so the contribution will become 0 from of all the splats which are behind this. Yeah. So based upon the density. But if you don't have, let's say this splat is semi-transparent, then these things also will get considered. So this is a very nice pictorial representation of NURF versus Gaussian splatting. So in NURF, as I was saying, right, you have to make so many cuts. Unnecessarily, you have to make so many cuts. Whereas in Gaussian splat, let's say if this along everything was a vacuum or only one surface was there, then ideally there will be only one Gaussian splat there, right? And I don't have to integrate and all that exhaustive stuff. I will just splat it and I will pass it through my alpha blending equation and I will get the final color, right? So that is why it is more efficient than NURF. You don't have to do any sampling, right? And another advantage of using Gaussian splatting is that it's actually very you can integrate it in standard graphics pipeline. So when this paper came, a lot of people they took this Gaussian splatting and integrated this in Unreal Engine, or if you are aware of such graphics engine, right? So the standard graphics engine like OpenGL or Chronos, they work on the concept of rasterization only. So this particular thing is actually very much integrated of what is been happening in the industry or in the graphics. Whereas ray tracing is very difficult, because in ray tracing you have to do for every pixel you have to create a ray and do that stuff, right? But here it is like it's actually very fast. So ideally you can integrate this 3D-GS into different rendering engines. And this is the loss, the differentiable rendering part of it. So you have a scene representation, you have a renderer, and just you take the rendered image and the ground truth image and you can take the loss. And another thing is in a training process of NURF, we don't, in one iteration we don't take the full image. We just sample some small pixels. Whereas in NURF, right, we can actually take, in one iteration itself, we can take a loss with respect to an image. So that is why the training time is also very fast. And why we do that in NURF is because otherwise it will exceed the memory, like so you will get out of memory errors and such things if you have more number of rays, because for every ray you have to have n points. So because of that the memory increases a lot exponentially. So yeah, that's it about the differentiable part of it. And the loss function that is used is a very simple loss function, L1 loss and DSSIM. So this is a standard way for reconstruction loss nowadays, so you can utilize this. So yeah, so
In this one, that's the SFM. Here, even even if we have the SFM, you said that some points may have Gaussians that are by mistake there. So we'll remove them, and some place we'll add them just because they need there. So if that is going to happen anyway, so we can always random initialize.
yes, so that is another thing. So another research direction is that why do we need SFM initialization? Can we randomly initialize and do the training process? So there is a work called a 3D-GS MCMC. So they make it as a sampling process, and their major thing is that even if you randomly initialize, you will actually reach or even do better than the SFM initialization. So yeah, there is one set. There are a lot of things. There are a lot of heuristics in this paper actually, from the SFM initialization, then the adaptive density control. So many heuristics are there, and people have actually solved those heuristics and came up with another paper or a good version of it. So yeah, you can actually do a random initialization as well. Only thing is that in 3D-GS it will take a lot of time, but in 3D-GS MCMC it will take similar amount of time.
The important part is that adaptive density.
Yes. So the crux is that how can you reach the surface as soon as possible, right? So suppose if I have points here and I want to reach that particular table, how can I reach quickly there, right? So that is the important part here. So there are a lot of works on this. So there are dash Gaussian, then there is even I forgot like what kind of works are there, but so many 10-20 works are there on just to improve the adaptive density control. So now we'll just touch upon this adaptive density control. So first thing is that we start from some initialization. So here in 3DGS from SFM initialization, but it can be random as well. But let's say we have SFM initialization. Now what can happen is you can have, so this particular thing is, let's say, the surface. Okay, let's assume that this is a surface and this was the 3DGS or the primitive that was trying to model this. So it is a scenario of under reconstruction, right? Because your shape is bigger but your Gaussians are not enough. So now what is the optimal strategy? That you clone or add more Gaussians near to this Gaussian. So you will add a Gaussian here and you will do this repeatedly until you model this surface, right? This is one scenario. Second scenario is that this was your shape but you actually model it with a very big Gaussian, right? And you don't want to do that. So what you will do is you will split it and you will do the optimization till it models the shape. So there are two scenarios, under reconstruction and over reconstruction. There is one more scenario. That is the pruning. Like what do I mean by that? So there can be some, like each Gaussian has this opacity, right? Alpha value. Can be that it is a transparent, because when you would allocate, like suppose you added a Gaussian here, then maybe next step you would have added a Gaussian here, but that is vacuum. Now ideally alpha for that would be 0. Hello. So alpha for that would be 0 and you want to remove that from your Gaussian mixture, right? Because it's an unnecessary Gaussian which has come there. You want to remove it from the computation. So that is called as pruning. So so there is a very heuristical way to find this out. So what they do is they check the positional gradient, and based upon this positional gradient, so we are taking loss with respect to the final color, right? So if my Gaussians are representing the scene very well, then this loss would be very less. So the gradients would be very less, right? In that case, I don't want to do anything. I don't want to touch this. But let's say my surface is of red color, but my Gaussian is predicting green color. In that case, or maybe vice versa, something like that. The loss is more, so the gradient is more, right? So this is how they kind of find out those Gaussians. They check the gradients of the with respect to the positions, and they check where the gradients are coming high. And based upon that, they check the scenario of under reconstruction and over reconstruction, because in both the scenarios, because of this, the loss would be high, and that is why the gradients will be high. So once they check this, then how do they check whether it's under reconstruction or over reconstruction? Basically, they check the covariance. If the covariance of a Gaussian is higher than some threshold, then they say that it is an over reconstruction scenario. It's better to split this Gaussian. If it is small, then they say that you have to now clone the Gaussian. So this is the process. So this is this particular part is what it defines. So densification, when gradient is greater than some threshold. If it is over reconstruction, you check the norm of your covariance matrix, then you split. If it is under reconstruction, you clone. And this is another scenario which is called as pruning. If your alpha is less than some threshold, you remove that Gaussian, right? And there is one more thing that they do. Every 3000 iterations, they reset the alpha values. So that is another heuristical approach that they do. That after every CK iterations, they will again reset the alpha to some number, so that you don't get stuck to local minima.
Is it like all the alphas?
All the alphas.
Aren't we losing the information by doing so?
No, then the next densification step will happen after every 500 iterations, right? So till then, those 500 iterations, that volume is fixed. So you will be learning the alpha values again. So it will automatically get resetted. So basically, like the concept here is that by chance if there is some false positive or something like that, some Gaussian which has come here which was not required, you can actually remove it through this kind of heuristical approach. So after 3k iterations you again reset everything, train it for another 500 iterations, and then check, then proceed normally. So what would happen is the Gaussians which would be good, they will in very few iterations itself they will have very high opacity value. So the opacity is learnable, right?
The waves were, the C was learnable, right?
No. Opacity is also learnable.
So once what you are saying is once we have found out the covariances and the points like means, the alphas are learnable faster. You're saying.
No. I'm saying that what would happen is if that Gaussian is exactly at the surface, it will get very high, like in very few iterations itself, even if we have resetted its opacity, the opacity will increase. Okay. Whereas maybe it can happen, right? There can be some Gaussian which can be at vacuum. Now because of whatever optimization steps you would have done earlier, but because of doing that you can actually remove those Gaussians. So it basically gives like it's basically done so that your so that your model, it doesn't get converged to a local minima, just for that. And if you see here, this is also opacity is learnable. And I think I skipped this slide. So this is the image formation model in 3D-GS. So let us just revise this. So this is, everyone now is familiar with this, right? This is for NURF. So you have C is I equals to 1 Ti alpha ACI. Now in 3D-GS also it's almost similar. So you have Ci, the color of a splat, alpha I is the opacity, and similar to the transmittance term. So if you see, this transmittance is 1 minus alpha. So you have this 1 minus alpha, and that's it. So instead of taking for 3D Gaussians, now you will take for the splats. So that is the only difference. So you don't take for a 3D Gaussian. So you will, first you have to do a splat process. So that means that you have to bring all 3D Gaussians with respect to this camera viewpoint, project them. So this is the splat, this equation. So you project them, so you will have some splats and then you will render them.
Before we reset those alpha values, do we clone the ones who are transparent or something?
Yes, we are doing that. So I think every 500 iterations, this densification step happens. So till in between those 500 iterations, nothing gets changed, like everything is getting learned. After that 500 iterations, they will do densification step. So this is like, this entire algorithm is very heuristics, like a lot of heuristics are there. But it, even after applying so many heuristics, it works, right? It's good, it's giving you better result than NURF. So there's one more thing, I think I'll just share the slide. So this is the rasterization part of it. If you're interested in like how this rasterization happens, because it involves some graphics, concepts, tiling and such things, you can delve deeper into that. So if you're interested in that stuff. So basically, if you're not interested in that, so you can assume that rasterization is one function which will take those splats and it will do an image formation for you, and everything is differentiable. So I think there was one paper which came recently which also tried to optimize this part of 3D-GS. So any questions here on 3D-GS? So we'll again summarize 3D-GS because that is very important. So what is the input we have? So input is multi-view images and camera poses, right? And SFM points, sparse points. Okay, that's the first step, that's your input. Now you will initialize, because you can't just start your optimization process with nothing, right? You have to initialize the points. So you will initialize 3D Gaussians at these SFM points. So the means will be the locations of those points of the 3D Gaussians, and you can have randomly assume the rotation, scales, and other opacity, all such things. Then what will happen? You will take one particular view from your training set. So you have some n views in your training set. So you will take that one particular view, and first what you will do is you will take this 3D volume and do a splatting process, right? For splatting process, what will you do? You will, sorry? Yes. This one, right? Yeah, this. So now, intrinsics you have to know that you will get. Extrinsics also you know, because you have run SFM. So you apply this and you get splat. Now with this splat, you give it to a rasterization thing. Now this rasterization is based on alpha blending, right? And with that you will get your image for that particular view. And then you will basically take a MSC loss. This loss you will take. This is called a reconstruction loss. Okay. After that, you will move on to another view like this. Then finally you will reach at a point where you have to do densification step. This is called a densification step. So here, first step is you will remove some Gaussians which are very large. Let's say you have so you make some assumption like my scene is this big. Let's say you have some Gaussians for which the covariance matrix is bigger than the scene extent, right? So you will remove that Gaussian. You will remove the Gaussians which have low opacity, right? It means that it kind of represents, it is representing a vacuum, so I want to remove it. And once you have this, you will now move on to the next part of it. You want to assign more Gaussians, right? So you will check what? But before begins, what will you check? Yes, so you will check whether the gradients, how good they are, what is the magnitude of the gradients. If it is very large, so you will do a densification. So if the covariance is large, split, covariance is less, clone. Okay? Once you have done, you have now again fixed your explicit volume, right? 3D Gaussian volume. Maybe it was 300,000 in this iteration, now it became 600,000. Again you run all the process again. And you will do it subsequently, and finally you will, in around 7,000 iterations itself, you start seeing very good results. And in 3DGS paper they say you have to do it around 3D for 30k iterations. And then what you will have is you will have a Gaussian mixture model for your 3D representation, and you can actually do a lot of cool things with it. And yeah, and it's pretty, and actually it is very intuitive compared to NERF, right? Because what you can do is, if you have a model, you will take that model, load in some viewer, and you can actually see that there is a Gaussian there, or there's some point there. And then based upon that you can do a lot of things. If you want, you can debug. It was very difficult to debug NERF. Like if some floaters were coming, it was very hard to debug those things. Whereas in Gaussian splatting, it's explicit, right? So you can do that. However, because of, it's not like that Gaussian splatting is very good, NERF is very bad. There are drawbacks of Gaussian splatting as well. First thing is it's like it consumes a lot of memory. So because it's a point cloud, right? Your point cloud can reach in millions. So you can imagine that what can be the size of this particular model. It goes in GBs. Whereas NERF was just an MLP, right? MLP, it used to consume around 200 MB or something like that, even less than that. So that's the one drawback of Gaussian splatting. Another drawback of Gaussian splatting is that because I was doing ray tracing, things like reflections, refractions, they were easier, right? If I'm ray tracing, I know that this is a medium, I can change the length, change the path of my ray. In Gaussian splatting, it is very difficult to do because everything is explicit. How will you now render or rasterize it through a different medium? So you have to do something different. However, there are techniques, but this is the major difference between these two things. And yeah, so but overall, the community of novel view synthesis, it has moved to 3D-GS. So if people who are working in this domain, they can use 3D-GS as their representation. So any questions? Okay, if there. Mhm.
For a single 3D representation, we have to train a single 3D Gaussian splatting model.
Yes, yes. So this is per scene. So for every scene, you have to do a Gaussian splatting optimization. So there are different now, even for this particular setting of novel view synthesis for static scenes, there are feed forward models. There are techniques like Duster, Master. So Badri here is working on that. So these are feed forward. So you don't have to do per scene optimization. So you will take some input views, you will give it to this model, and you will get your Gaussian splats. So you don't have to do training as well. So you have to do training one time. So those things are also coming into picture now.
Are there foundation models for 3D or?
They have started to come, like Duster is one such model. Then there is VGGT, which recently came. Anything, yeah. So for scene level, these are the two foundation models. Okay then, I think, thank you. Thanks for your time.